All right, so we have the axes. We're adding heat energy across the x-axis. That means that when we start here at the origin, as we move to the right, we are continually heating this up. We're adding heat. So a good way to visualize that would be to take a pot and put some water in it and put it on your stove. Okay, as time goes by, you are continually adding heat energy. But what about the y-axis? Okay, so the y-axis is going to be measuring temperature, and you always want to say what unit you're using. So we're in degrees Celsius. Okay. All right, so we are going to be watching water change its state, and so we're going to start with the water here on the y-axis at this point right here. Okay, and that happens to be below 0 degrees Celsius. So there was one question that a student had, and they said, Mr. Ashley, I thought that ice, solid water, was always 0 degrees Celsius. And the answer to that is no, it can be lower than that, okay? Remember, temperature, 0 degrees Celsius, is just a measure of the kinetic energy of a substance. So 0 is just a number, okay, on the Celsius scale. It's where water melts and where water freezes, okay? But you can actually have the molecules of water moving at a slower rate than when they are at 0, okay? And that takes us down into the negative category. So you can have ice that in this case would be at like -5 degrees Celsius. It's colder than 0. It's just a matter if you took more and more energy out of it. All right, so we're starting with this solid ice at 0, and we're going to take it, and now actually if we were in my classroom, we have a lab where we would actually do this. We're going to heat up that ice cube, and we're going to measure its temperature every, say, 1 minute. Okay, so here we go. We can predict that it will increase, but it does something funny. When it reaches 0, the temperature no longer goes up, even though we are still adding energy. So you can see what one student called the first plateau. And it's at this plateau that the temperature stays constant at 0. Very strange, okay? So let's label some of the parts of this graph so that you have a better understanding of what's happening. So from below 0 up to 0, the ice is in the solid state, or the water is in the solid state, okay? When it hits this plateau, we observe it, and we notice that there is both the solid state and the liquid state. What would that look like? Well, it would look like the ice cube floating around in liquid water. And if you kept adding heat at that point and you had a thermometer in there, you would notice that the temperature does not change, okay? Now, there were many of you who in your homework answered, yes, of course it changes. It's getting hotter. Well, that's the thing that is a bit of a surprise. The temperature will stay at 0. Now, we'll come back and we'll describe why that happens in a second, but let's continue on with our little trek, okay? So, we've warmed the ice cube. It's reached 0, okay? At that point, it's doing something called melting. So, I'll go ahead and put that in here. And if we were going in the opposite direction, it would be called freezing, right? But in this case, it's melting. And when it all turns to liquid, it begins to increase in temperature again, okay? All right, so at this point right here, all right, I'm going to go ahead and circle this, and I'm going to highlight it to make it easy for you to see. We have kind of a special temperature right here, okay? And that temperature is the melting point of water. So 0 degrees Celsius, okay? And it's important to say that we're at sea level pressure, okay? So we're at 1 atmosphere of pressure. This is called the melting point, or conversely, the freezing point, okay, of water. All right. All right, now once we have all of the water has been turned into a liquid, the temperature starts to go up. So here on this slope, everything that we see is in the liquid state of matter, okay? So to make it easy for you to see, let's go ahead and highlight this in different colors here. We have the solid phase, we have the liquid phase, okay? All right, so as you can see, the temperature is climbing the hill, okay? So the temperature is increasing as we move to the right and continue to add energy. But then something even crazier happens. We reach a point where, again, we get a plateau. And I want you to look at how much larger this plateau is than the melting plateau. This plateau is much larger, all right? And what's happening here? Well, at this point, we see that the liquid water is beginning to form gas bubbles all through it, from the bottom all the way up to the top, and we call that vaporization. Actually, there's two words you could say. You could say that the water is boiling, or if you want to be technical, that is the water is vaporizing, okay? So the water is boiling, changing, okay, from a liquid to a gas. So you're going to see both phases. You're going to see a liquid plus a gas up here, okay? All right. Now, notice that the temperature doesn't change. So what temperature is occurring right here? Well, if you were to measure it with the thermometer, it would be exactly 100 degrees Celsius. And the curious thing is that the temperature would remain constant at 100 degrees Celsius until all of that liquid water was gone. Oops, that's not what I want. All of that liquid water was gone. Let's fix this here. And the water began to change into the gas phase. Okay, guys? So here we go. Once we're in the gas phase, I want you to take a look at what happens to the temperature. The temperature continues to rise. There was a question in your homework. It said, which state of matter can possess the highest temperatures? And a few of you got it right. It was the gas phase, okay? And so we need to talk about why that happens, all right? So to understand that, let's go back down to where the water was in the solid state, okay? So when you see this water in the solid state, what you would see, if you could look at it, would be molecules in a very orderly crystal structure, okay? And they're in that ordered crystal structure because they are bonded to each other by intermolecular forces. Now, we talked about that in the last lecture, and that these are important. They're little attractions between the molecules that kind of hold them like the bricks in a wall, okay? All right, now as we add heat to that solid that you see right here, this ice cube, as we add heat to that, these molecules begin to vibrate. They begin to move with more and more motion, the more energy you add to them. They're vibrating, okay? And what happens then is eventually they're going to have enough energy to break the intermolecular forces, and now those molecules are sliding over each other. So what they're going to do is they're going to form into a liquid. And we see that when the molecules are still touching each other, but they're able to slide and move over each other, okay? That would be in the liquid state. So the plateau that you see right here, where you see both a solid and a liquid together, in this plateau, the energy is being put into the solid and liquid, but it's being absorbed by the water that's in the solid state, and it's breaking the remaining bonds between the molecules to turn into a liquid. And it will stay at the same temperature until all of the solid water's intermolecular forces have been broken, and now the water is in the liquid state. Okay, and so here we have it. Now, if you look up here at the plateau that's between the liquid and the gas state, it seems a little bit strange that it's so much larger than the one that's down here for melting, okay? And the answer, the explanation for that is that to go from being a liquid to a gas, okay, I gotta trap the gas in a balloon here. In a gas, the molecules, every single one of them, 100% of them, have to be not in contact at all with their brothers and sisters. Okay? So that means that a lot more energy had to be entered into the liquid to turn it into a gas state. That's why that plateau is so much larger. Because in a liquid, you only have to break a few bonds to allow the molecules to slide past each other and be called a liquid. But in a gas, 100% of the molecules have to break every single one of their bonds. So it takes more energy, okay? And that's why that plateau is so much larger. More energy is required. And you could see that. You know, so if that was on a test and you look down here, you could see that from here to here, this is much more energy that is required than from here to here, okay? I'm marking it in yellow. That's much less energy, okay? It takes more energy to make something go into the gas phase than it takes to make something go into the liquid phase. That's because the molecules in the liquid phase are still touching each other. Okay, so that's moving up from the bottom up towards the top. Okay, so that's going in this direction. Okay, guys? You see that, right? Okay. So moving from the bottom to the top, taking it from a solid to a liquid to a gas, the one thing that was common for each of those steps was we had to add energy. And so we have a special word for adding energy, for putting energy in, and that word that we use in science is endo. That means in. Like your endoskeleton, you as a human being have a skeleton on the inside of your body. That's your endoskeleton. Where a crustacean like a lobster or an insect like a cockroach would have their skeleton on the outside of their body. That's called, and I know you're all raising your hands, it's called an exoskeleton. So endo, we put energy in, means that these are endothermic processes. Now, if you're making the prediction that that's going to be on the test, you are correct. Okay, you will see that on the test. And so, like I was saying, make sure that you make really nice notes for yourself. Oh, that didn't come out so nice. Wait a minute, we could fix that. Let's fix that. We'll change this. All right, so this is an endothermic process as we go from a solid to a liquid to a gas. You have to put energy in. Now, if there's energy going in one direction, the law of conservation of energy says the energy you put in has to be equal to the energy that comes out. Moving in the opposite direction has to be energy coming out. So if endo means in, then the word for out is exo. So these are exothermic processes. Okay, guys? And in these processes, energy is released. Okay? Oh, that's not what I want. Come on. Here we go. Energy is released. All right? And so, because these are notes and we want these to be helpful for you, let's say that I'll just say this is energy in, and this is energy out. Okay, guys? All right, so let's talk about it. What would be some processes that released energy as they happened? Well, it would be the opposite of boiling or vaporization. So what is the term for the change of state that when you see a gas becoming a liquid? I know you're raising your hand, and that is condensation. Okay? And that is when we see the gas molecules, they begin to slow down. For a number of reasons, you could take away their heat, right? You could cool it down, and the molecules are slowing down, and then they eventually begin to rub up against each other, and because they're so close, they form intermolecular bonds, and they become a liquid, okay? Now, that's going to happen here in Imperial Beach, tomorrow you're going to see rain, and that's liquid water coming from the gas phase of water that's in the atmosphere. And that's because we have a cold front coming. It's cooling down the warm, moist air that we have, making the water molecules touch each other. That forms raindrops, and then we get rain, okay? So condensation is an energy releasing process. Energy comes out, and we call that an exothermic process. All right, so as we go down, the liquid can be cooled even more. You take more energy out, okay? And eventually you're going to take out enough of that energy that those water molecules are moving so slow that they form intermolecular bonds in all three dimensions around them, and you get what is called, not melting, the opposite of melting, you call it freezing. Okay? And that is also an exothermic process. So you have endothermic, adding energy going up, and you have exothermic coming out. All right, so what have we talked about today? Well, we clarified why the plateaus are there. And we also discussed why the plateaus are of different size, and we related that to the intermolecular forces that exist in each change of state, okay? And we then introduced two more terms, endothermic processes and exothermic processes. And we discussed what that means in terms of the changes of state. So this is the heating curve of water at 1 atmosphere of pressure. And guys, you're going to want to have this handy when you take your exam, because there's all different types of questions I can pull from this. I just remembered there's two more things I need to add. There are some oddball changes of state. For example, you can have some substances that can skip being a liquid and can go from being a solid directly to becoming a gas. And we call that, I know you're raising your hands, we call that sublimation, okay? The compounds that do that are almost completely nonpolar. They don't want to be a liquid at all, okay? So sublimation, and then in the reverse direction, a gas directly to a solid. Here it is. Oh, I just kind of made a mess there. This is called deposition. All right, guys. All right, so that's a bit more information for you and some clarification. Keep this safe, and please do use it on your exam when it comes up.